Thank you.
Hang on. Okay. So obviously shout if you can't see or anything like that. And I'm happy to be stopped at any point if things don't make sense. But otherwise, I'll just try and go through at a reasonable pace. And I've kept this relatively not sort of hyper technical, because I don't think that's necessarily interesting for everyone. And so yeah, so what I'm talking about today is an epidemic on cassava. So cassava is a staple crop in sub-Saharan Africa. I'm sure lots of you know that, and lots of you have probably eaten it. And so it's grown across the continent, very important across the continent. But the two things to point out are the DRC is the world's highest per capita consumer, and then Nigeria, further west, is the world's largest net producer of cassava. West Africa grows an awful lot. And so since 2004, there's been an epidemic called cassava brown streak disease, or of cassava brown streak disease, spreading. It's been spreading out of Uganda and into neighboring countries pretty rapidly, and then heading out west and south. So these are some of the very sparse reportings that we have. You often hear, more informal stories about how bad it is in various areas, but the formal reporting is very bad. And you can see here a picture of what the disease does to cassava. So these are the roots. And can you see my mouse, by the way, Francesca? Yeah, you can. Yeah. So these are the roots that should just be white, pure, sort of starchy, potato-like, and this is necrosis caused by the disease. And so the most important thing to understand from an epidemiological perspective is how this thing spreads, and it has two different mechanisms. So the first is the vector, the whitefly vector. So Bemisia tabaci feeds on cassava, and then the virus gets into its mouth parts and it flies to a different plant and introduces the virus. And so that's relatively local. That'll be bulking up within a single field, within a single farmer's field, but also then spreading locally, maybe to neighbors' fields and things like that, through windborne dispersal. The other mechanism is through cutting transmission. So cassava is vegetatively propagated. So what that means is when you get to the end of a planting season, you chop down your plants and you chop them up, the stems up into small pieces like this, and you then replant them in the next season. And so what that means is if you had a virus in the last season, you still have it in the next season, right? Unlike seed planting, where you kind of hit the reset button, this persists. Which is, and what that means is then if you move these cuttings, which is a very common thing to do, you'll replant your own cuttings, but you'll also share with your friends, family, buy some in the market, right? And this gives it a longer range mechanism of spread as well. And so you have these two mechanisms going on. So what is the role of epidemiological modeling in this system and trying to help here? So modeling isn't everything. There are things that need to happen in the real world. There are things that modeling can do to help make you more strategic, reduce the uncertainty around certain questions. So one really critical one is the data is so sparse here, right? Like data on COVID was bad enough in say sub-Saharan Africa, and let alone when you're talking about an epidemic in plants, right? Like there's not much focus on this, and that means that you not only do you not know sort of where it will spread in the future, but you don't even know where it is currently necessarily, right? You've got these little snapshots of where it is, but you don't fill in the gaps. There's these huge gaps in between these very sparse observations, and so it's very important to know where it is right now. It's then important to know where it will spread in the future, at what rates will it arrive in different countries, so that policymakers in those countries can kind of calibrate their response to the estimated arrival time and know how long they've got to get prepared. And then when you start to think about, so when you're thinking about it arriving, where should you be looking for it to arrive? That's a question of limited resources and where you put those limited resources, for your surveyors to go out and try and spot this early. And as most people will know, like the earlier the better when it comes to epidemics, because that's when you really have a chance to actually do something at minimal cost and minimal impact. Once time goes on, things can get out of control pretty quickly. And then a final question is, again, a question of limited resources and the optimal use of those limited resources to deploy management to actually try and control the disease. These are the kinds of questions that you can address, and I'll be talking about most of them today. Okay, so I'll sort of take you through the story of what we've been doing though in the development of the model and then subsequent use of the model. So where we were starting from was we didn't have any data about where CBSD was or how it was spreading. We knew the epidemic had started in 2004 and various people had been doing survey work. So we had collaborators in East Africa through the Cassava Diagnostics Project, which is a consortium of sort of 7 odd countries. But the historic data collection was all on paper forms like this, right? And so this is kind of the reality of working on a problem like this. And it hadn't been digitized, or if it had been digitized, you didn't know whether you could trust the digitization. And so an initial part of the work was simply, we were sort of hunting out where the data was, and running digitization workshops with our collaborators, with the scientists, to get the data in a usable format before you even know what's there, right? Before you even know whether it's useful. You hope it is, but you don't know. And at the same time as this East African project was happening, there was a similar Gates-funded West African project. And we were very keen at this point for this problem not to keep happening, right? Because it not only, it just causes issues at every level, right? You don't trust the quality, you don't know how long it will be before you can get hold of the data, all of those kinds of things. So we work to develop a sort of simple digital form and train scientists at every opportunity to use that. And we did actually have amazing uptake. Every single one of our collaborators started using the digital form, and sort of from that point onwards, all sort of 14 odd countries were collecting data digitally. And that's still going on to this day. And so this is an example in the field doing training in Uganda. Okay, so we got hold of the data, and so then building up the model. So what we have is a landscape scale model. So we're looking at Uganda here, and the key parts of the model are these data-driven layers. So this comes from an epidemiological understanding. You think about what pieces of the system really matter in terms of modulating the spread rate. And so your foundation has to be where is cassava grown and in what volumes, right? And so Anna, who was with the lab, developed this cassava map, which is a map at a 1 kilometer resolution across the continent, using host production data to say how many fields are in each 1 kilometer square. So that's the base of our model. We then have data on the abundance of the whitefly vector that's fed in as well, and that comes from the survey data. So they weren't just looking for where disease was and weren't just recording where disease was, but they were also counting how the abundance of the disease vector, the little fly. And so those are the 2 data-driven layers in the model. And then the third piece that we have is that digitized surveillance data. So here we're just looking at Uganda. And so, as I said, the epidemic started in 2004 in Uganda. And so that's where we have this really critical this disease progression, where I'll click play here, and you'll see, so red is disease positive presence and green is disease absence for CBSD. And so you'll see that they go to different places each year. We're stepping forward a year each time, and you can see the disease intensity growing in Uganda. But what's challenging for us, and challenging sort of from the methodological perspective, is the fact that they're not going to the same places, right? You don't have consistent coverage of the whole country all the time. You have jumping about, which means you can't necessarily see what's changing in one place over time. But this is still a very a critical and relatively good data set for this kind of work. And so here I'll go into just a little bit of detail about the model parameterization and validation. So the next steps, once you have you've kind of agreed how your system works, how the model is set up, you then need to tune your model. So parameterization, you need to tune it to the real data. So how fast was the disease spreading effectively? And we used a technique called approximate Bayesian computation, ABC, which is a computational technique, Bayesian technique, to tune these model parameters around the dispersal rate of the epidemic of the virus. And what we did, or what is essential, is to not show not use all of the data for the training for this parameterization step. We showed it half the data just from 2004 up to 2010, and used the remainder of the data from 2010 onwards to validate the model. And what we're looking at here is a simplification of that raw data I showed you last time. So this central region here is this curve. And what you can see is how the proportion of the surveys that were infected goes up over time. So it very rapidly bulks up in that small region, which is where the epidemic started, and then drops a little bit here. And this is actually the result of a intervention program that they ran for a few years, but then bounces back up when they stopped doing that program. And we parameterized that separately as well. And then at the rest of Uganda, so ignoring that central region, but the whole other region, you have the same statistic for what proportion of the surveys were infected over time, and you can see that growing at a slower rate nationally. And we have a third statistic as well, which is kind of tracking when the epidemic arrives in these sort of large regions. And this is the point of this is to reduce kind of the complexity of the target data, because for computational reasons you have to do this, and so you have to simplify the raw data and look at some key dynamics like these bulk up rates. And so this is then the validation, so against the unseen data beyond 2010, and you can kind of see at a glance that these are two very similar plots. This is without some constraints, and this is with constraints, but effectively running the parameterized model from 2004, and you get this. The blue is the breadth of predictions, right? So it's tracking the red, which is the real data, very well. It's very encouraging that the model is actually picking out the right signal, and is certainly in the right ballpark of what happened in the real world, and the kind of median trajectory is very close to the real data, which is a very good sign. And if we look at a few examples of what that actually means, so this is a single simulation here, and it's looking at the surveillance data. And on the left is the surveillance data that I previously showed you, what was actually collected in the real world. On the right is an example of what the simulation predicts, right? And so this is starting in 2004. You've got your model parameters now, and you just hit run, and this is the yearly snapshots, and you'll see that it's not doing. You would never expect it to be identical, but what you need it to do is to be capturing those general dynamics and bulking up at the right rates in the right regions. And it really seems to, at a glance, right, and through our validation statistics, it is behaving well. Okay, and so then we can go on to questions of predicting the present and future distribution. So we now have our model set up, and that's the tool that you can then use to answer these questions. So this is a single realization, and just a single example of how the epidemic could spread from the parameters that we have. And you'll see it spreading through central DRC here, and then coming into this very high density region in West Africa. I'll just play that again, because you can hardly see it starting here in Uganda and then rapidly spreading in the higher density regions of Rwanda and Burundi. Gets into this higher density region, and you just get these little hops, and then once it gets to the high density region in West Africa, it really takes off again. There's an important point here that I won't dwell too much on, but it's around, because this is a stochastic system. We have uncertainty on the parameters, and then the model itself is stochastic. So there's variability in the outputs due to inherent randomness in the system. This is a hard point to communicate, especially to policymakers, because you wish you just had one single result, and that was definitely the version of the future that was going to happen. But actually, we don't know for sure. There's a lot of different parameters that do describe what you've seen in the real world up to the present day. Okay, so what this video shows here is a 2D plot of two of the critical dispersal parameters, and each frame that you see in the film is a different version of the epidemic, all of which do match the data that we've seen up until the present day. So on an early slide, I showed you it arriving in Rwanda, arriving in Zambia, and arriving in central DRC up in 2017. All of these snapshots tick all of those boxes, but because of the low quality, not low quality, but the lack of data, we can't narrow down further our estimates of exactly what's going to happen in the future. And this means there's still quite a lot of uncertainty. And so each snapshot is going to be a different simulation, and the colors show a different decade. And so this is sort of early spread, and then the red is sort of later spread. So, and they're ordered from smallest epidemic to largest. So the key things to just draw attention to are the impact of parameter uncertainty on the variability of what the real world epidemic could look like. And you'll see around halfway, about 50% of the epidemic's realizations do actually reach West Africa, and about 50% don't. And so you've got this, and that's clearly a very critical sort of fork in what could happen in the future. What we can do with this from a communication perspective, you can kind of collapse this down for people from whatever region or country they're from. You can do this at a regional scale or nationally, but you can give box plots of the most probable year of arrival in a certain place to give people a ballpark. As time goes on, as more observations are reported throughout Central Africa, we will be able to narrow down this uncertainty. But as it stands, this is kind of the uncertainty that we have. And yeah, so those are the predictions and for the arrival times in the different countries in West Africa and beyond. Okay, so that's a bit of a deep dive on predicting the present distribution and the future spread rates. But the two other questions are, where should countries be looking? You know, because it could, as those predictions show, certain simulations arrive sooner, certain arrive later, but where should they be looking to spot it as soon as possible? And one complication in this whole picture is that I described the two mechanisms of spread at the start, which were the whitefly spread and the cutting spread. And most of the time, all of that is very local, right? Sometimes the cutting spread will be a bit longer range when people take things to markets or drive them somewhere. But generally, we're talking about local spread. But if you're in Nigeria and worried about the disease arriving, you have this gradual cross-continental scenario, which I've been showing. But there is also the probability, which is hard to quantify, that somebody could get on a plane and directly introduce the infected cuttings straight into Nigeria today, right? And so there are phytosanitary measures in place at airports and things like that. But I think there is this challenging and hard to estimate issue of whether people will be doing that and where they would take it. And this is just an example that just from Googling, you can see that humanitarian organizations, for example, have in the past flown cuttings around to different communities who need planting material, and so you can see how that could be a huge jump in where the epidemic can get to. So if we just put that's a complexity around where people should be looking. So if let's say you're in Nigeria, where should you be looking? Should you be looking around the airports, or should you be looking around the eastern border where it's spreading across the continent? If we just park that for one second and focus on that cross-continental scenario. So what we take here is the outputs of the model, and that range of different routes that it could spread to Nigeria, and that gives us the various entry routes, and therefore we can optimize for where you should be looking to spot any of those entry routes. What gives you the best chance? And so this is just an example, and this is very much work in progress, but this is an example of a stochastic optimization algorithm to try and answer that exact question of across all of those realizations, where should you be going to survey to give you the best chance of detecting arrival within the first year of it arriving. Because at the moment, the surveillance that's going on in West Africa is actually, they're going kind of uniformly across the country. And so there's a good chance that is not the best way to spot the disease arriving in your country early. When it comes to the question of the direct introduction scenario, my sort of current best thinking is that there is a shift in strategy that you would want to do. So if you're a very long way away from the epidemic arriving, if the prediction is it won't arrive for another 20 years, like there's less than 1% chance it'll arrive for 20 years or something, then you want to be worried about this direct introduction scenario, and that's what you want to be looking for. As time goes on, you want to be shifting from that strategy towards the more likely cross-continental scenario. And so what we're trying to do is formalize those two strategies and how you transition from one to the other, and importantly, finding ways to communicate this in a sort of simple and practical way that people might actually be able to use, rather than overwhelming people with this stochastic stuff. Okay, and then the final piece on the cassava question. So this is the next phase of work after we've finished working on the surveillance question, but it's thinking about what management options actually exist. What can countries, individual farmers actually do? And so the ideal solution, and that's being worked on, is to have resistant varieties of cassava that are resistant to CBSD. But currently there are no African varieties. All of the tested varieties are susceptible. There has been some work, so cassava is originally from South America, and there has been some work that's identified potential resistance in South American varieties, or a South American variety, but that particular variety doesn't do well in Africa, and so there would be work to do to try and introduce those traits to African varieties. But in the coming years, hopefully there will be resistant materials. But in the meantime, whilst those options don't exist, what can people do? Are there sort of other strategies or combined strategies that countries can do. And so one interesting, again, this is just an idea, so I'll share this thought with you, which is a recent paper was quantifying the impact of pesticide use, of low-level pesticide use on the abundance of the white fly, and therefore the spread of the disease, and had very positive results from, and even very good results from simply dipping the cuttings in pesticide prior to planting, and then doing no subsequent spraying. Of course, there are risks of using pesticides, and I'm not an expert on this front, so I'd certainly be speaking to the experts before making any big recommendations. But I think the reason why this is at least exciting for me is that, unlike a lot of other potential management options, it doesn't rely on like complex infrastructure being developed for sort of clean seed systems and things like this. And it also could work sort of on an individual level. It doesn't require farmers to coordinate their behavior to get benefits or things like this, which are very challenging to achieve. And it doesn't require farmers to necessarily switch their varieties, because people have a lot of, for various reasons, for taste, certain qualities of their specific varieties that they won't want to switch to. So even if you did get a resistant variety come along, it might not have the right taste traits or starch production that people actually want, and so they might not switch anyway. So I think what really needs to be at the center of thinking about these management options is what will people actually be prepared to do, when you've got very limited capacity to train people, to persuade people to do stuff anyway. What can you do in those circumstances? Okay, but that's the next phase of work, is working on the management options. And finally, as I mentioned at the very start, I have this totally different aspect to, well, not totally different, slightly different aspect to what I've worked on. So as I came to the end of my PhD, I also was very interested in these market access problems and how those incentives for the farmers often don't work. People might want you to buy improved varieties and grow more, but if no one's going to buy the additional crops that you could grow, why would you produce more? Things like this. And so the market at the lowest level for smallholder farmers is often very exploitative and doesn't work very well. And so me and some colleagues during my PhD, we set up had a startup and managed to get some funding to go and develop a digital marketplace out in Colombia, which I did for 2 years. And so we built the whole platform and managed to get a few thousand users. People still using it to this day, which is great. And so I'm happy to also speak if anyone has interest in sort of market access questions as well. I'm always very interested in that. So yeah, just quick thanks to all of the funders, the Gates Foundation, collaborators, but specifically Rich Stutt here in the Gilligan Lab, and of course Chris Gilligan in the Gilligan Lab. And all of our collaborators in Africa, the WAVE project in West Africa, the CDP in East Africa, and the Ugandan team as well. And there's my email. I'll leave that slide up for a second in case. Okay.
Thank you so much, David. Thank you.
All right.
Big clap from me. Very quick question before, because I'm conscious about the time as well, and I don't want to monopolize. Just a quick question to clarify. The intervention program that you referred to that showed a positive impact, what was it? And could that be adopted as a solution?
Yeah, so that was clean seed programs. So again, whilst resistant varieties don't exist, what people might do is try and find a part of your country that has the lowest level of disease pressure, and grow a lot of clean material, and then either disseminate for free, so give out to farmers this clean planting material for free, or try and get the economic incentives to work for the farmers to buy some of those cuttings because they'll get higher yields. And the issue with that whole system is that whilst they're not resistant varieties, your stuff will get reinfected within a few years. And so that's why you saw that bounce back up. As soon as I assume they were giving those out for free. I think that's what they said. And so once you stop doing that, then everything gets reinfected again. It's not. And so people were looking into trying to set up that economic model where you'd get local producers to sell it out to farmers, but that does rely on farmers seeing the value of this, and the materials that they're giving out actually being resistant, right? Because you can't see when you've got these stems whether they're infected or not, right? You go and buy them from a legitimate trader, and it turns out they're just as bad as your ones or worse.
It's the internal system, but you mentioned that the problem in particular is in high density regions. So high density, you mean population?
Well, high density of production, cassava production,
right, okay.
Yeah, sorry, which is very, in rural areas, very, well, outside of cities, population's very correlated with cassava production because everyone grows a bit, and yeah, so.
Okay, I have other questions and comments, but I'll hold on to them for now. I like to ask others to contribute and ask questions and make comments, please. Who would like to be the first? Martin, please.
Yeah, thanks very much for a great talk, David. It's slightly kind of peripheral to your core work, but as the output is encouraging this very widely used insecticide, I guess one of the issues is how that the collateral effects of increasing the amount of insecticide in poorly known ecosystems, and I guess I'm thinking about pollinations and so forth. I mean, I suppose, yeah. Any thoughts on that?
Yeah, well, so this is that thought of that strategy only popped into my head after seeing that paper published very recently. So I had the same concerns around, what would this actually mean on the ground, right? Like what level of insecticides are currently being used? I mean, people generally previously dismissed the idea that insecticides could be a solution because people can't afford them anyway. So I think they're probably not used very much at all. The appeal of that idea, again, very superficially, is that if just soaking the cuttings in insecticides and then planting them rather than spraying it all over the fields later on could have an impact at that early growth stage, that seemed, again, superficially to be have a minimal impact. But one thing I should say is this is not the only option on the table. It's the one that people haven't been talking about, and it seemed exciting for a few reasons. But the other options people have, and that should be done in coordination and irrespective of whether pesticides are part of the picture, are training the farmers so when you're harvesting, if you can be selective in which cuttings you then choose to replant for the next year. So keeping track of the yield that you got and the quality of the yield you got from a certain plant, and replanting only the ones that are uninfected, that can have a huge impact on keeping your whole field clean for much longer. The standard practices of just removing clearly infected plants from your field quickly, that can also help. So there's basic things like that. They all rely on some degree of training, and the strength of the extension system is in different places will vary a lot. So certainly pesticide is not the only option. Then there are also different varieties respond differently. So some are not as badly impacted as others, right? And so if you can make those varieties more widely available, then the impact of this will be less. And even thinking about doing that in advance of it arriving in your country, right? So if you can subtly swap out what people are growing towards ones that will be less badly impacted, by the time it does arrive, the impact will be smaller and therefore more manageable. So there's all kinds of more benign things that are certainly in the mix.
And David, sorry, would intercropping be also a solution? So growing these cassava varieties with other plants, which might attract perhaps or reduce.
Yeah, it certainly could be. I've seen some studies looking at that. I mean, I don't think it's going to totally save you from because these white flies are pretty abundant, and it doesn't take much for them to spread it around in your field. But yeah, absolutely. I mean, I think the intersection of lots of these strategies, until lots of resistant varieties come along, is going to be the solution. But the intersection of ones that are most easy for farmers, or farmers most receptive to adopt, right?
Which plant would be the one that farmers could use?
I don't know off the top of my head. Yeah,
Maybe
there
somebody
definitely
here
are
who
studies.
does might know this.
There definitely
Okay.
are papers out there looking at that. Yeah,
that's an area to explore perhaps. And then Ellen, and then John, please. If you would like also to say where you're from, that would be great.
Hi, Jean Ristino from NC State University. Give my regards to Chris and Nick. I'm familiar with the cassava work, and a couple questions. First of all, I know the Gates Foundation has funded some work to look at sensors for disease detection, since the path that both cassava mosaic and cassava brown streak are moving in the planting material. Knowing whether it's infected or not can really stop spread if they're deployed early. And then the other comment I wanted to make is that brown streak spread because cassava mosaic resistant varieties were deployed that were very susceptible to brown streak. So your comment about humanitarian efforts and how they can cause epidemics, this is like a classic example. And what are your thoughts in that area?
Yeah, no. So I think that is the early on in. Well, so the background is prior to this cassava brown streak disease epidemic, there was a severe cassava mosaic disease epidemic that's also spread across from east to west Africa. And yeah, my knowledge is at the time they quickly disseminated varieties that worked pretty good against that original disease that turned out were incredibly susceptible to this new disease. Of course, that does a lot of harm to people's trust if you've worked hard to give out these varieties and then put people in a worse situation. The one area where I'm cautious is that I think because of the sparsity of data. I mean, one of the biggest frustrations for me is that you have so many confounding factors around like differential varietal response to these diseases, but then nobody knows where these varieties are planted, right? So even if you know how all of the different varieties respond, you don't know where they are. and so there's all of these confounding factors. And so I'm also cautious to correlate too strongly just one thing over another, right? Like, so I'm sure that certainly played a factor, that early intervention in the rate of spread in that region, but it's spread probably far beyond there now. I don't know whether it would have been sort of essential for the epidemic to start in the first place. It's so hard to know those things, but the general principle of caution on behalf of NGOs is incredibly important, because they have the ability to get past regulations that normal people don't, right? They do have planes, and they do have big trucks that they can ship around huge amounts of planting material. And so yeah, I haven't personally engaged much with people in that world, so I suspect there's not much awareness of that. Yeah. In terms of the sensors, yeah, I don't know what the absolute latest progress is on kind of remote sensors for detecting infection in the cutting material, but yeah, the more that you can, if you can have something that can quickly and cheaply tell you whether a cutting is infected or not, and you can just get rid of that would be also miraculous. Yeah, and obviously people have looked at various diagnostics, but you know, as with all of these things, they're generally a bit expensive or nowhere near cheap enough to be used at scale in these countries.
Yeah, and I think the sensors that have been developed now are for mosaic virus, and they're looking at hyperspectral images of leaves, so in older plants. And then by that time, the disease is already there. So capturing cuttings is.
Yeah, absolutely.
Yeah, thank you, Jean. Ellen, please. I think you're plant sciences, right? I think you're muted, Ellen.
I can't hear you.
If you're not muted, loudly, no, you're not muted, but we can't hear you. Sorry. Try again. No.
You can come in this room if you like. Ellen's like 5 meters away.
Okay.
Yeah, just come through into the.
So walk down the corridor.
Yeah.
David, in the meantime, while we're waiting for Ellen, I was thinking we could maybe contact the Wilfred program and perhaps create some kind of training.
How can they hear me?
Yes, we can hear you. Yes.
Yeah.
Okay. Well, you're here. Oh, I was just going to ask. Yeah, which is really weird. When I was seeing your predictions, you know, like you said, you didn't have very good data, and the predictions often kind of when the disease is going to arrive in a country often span kind of like 20 plus years.
Yeah.
Is it hard to get people to actually, you know, act on things when you can't give more kind of precise predictions and estimates? And have you had, you know, a good response from people when you're trying to tell them about it?
Yeah. All right. I'll see you on the other side. Yeah. Well. So the uncertainty. Well, no, I'll wait for her to appear back now so you can hear my response. The uncertainty, I think, increase that the further out into the future you're going and the further away the country is, the greater the uncertainty around the arrival time is. Whilst whilst there might be a broad distribution, a lot of the time the majority are around a certain time point. But what I would hope to do is to try and provide people with countries with recommendations that work no matter when it arrives, right? So if countries are already going to be doing some level of surveillance, right, then the way that you would just guess to do that will not necessarily be the best way to do it every year. So if you're going to be doing that anyway every year, then we can give you recommendations to try and optimize that. Another way into this is, as we touched on a minute ago, there's another disease, cassava mosaic disease, and that also greatly reduces yields. Is another of the factors that stops cassava production being as high as it should be. If you can make sure that your interventions work today for cassava mosaic disease and are also then really good for CBSD, you can get kind of sort of different infrastructure in place, right? If you can, I mean, again, not to stick on the pesticide point, but that strategy around pesticides would work just as well for cassava mosaic disease, and that would work from today. And so if you get some training and capacity in place, the same with roguing, the same with these different things, that they work for both diseases. And so if you can get that capacity in place today for that disease that's impacting people today, and therefore more important to policymakers, you can also get that kind of training and knowledge and capacity in place for the incoming other threat. That would be how I'd try and. Oh, the other thing is, as I said, you can also narrow down that uncertainty over time as more observations come in from across sort of West Africa.
Thank you, Ellen, for the question. Do you think, David, that we might also need to build capacity in the countries themselves so that they take more ownership of the issue and in a way, find the solutions according to what they really need and what they perceive, and then might have longer lasting effects? It's more international development point of view.
Yeah. So, well, I don't know whether it counts fully as entirely national, because it still has the Gates funding, but say like West Africa, the WAVE project in West Africa, this consortium across Central and West Africa of countries that we work closely with, and they're the scientists on the ground collecting data in West Africa. Yeah, of course. This, I mean, and they are pretty close to the politicians as well, which is obviously critical, because they'd be the ones ultimately deciding whether to prepare for this and how seriously to take it and everything like that. Yeah. You have to.
Yeah.
I mean, and that's always the challenge, right? Because we're far away, and like even further away from the farmers, right? And as I found, like with my work in Colombia as well, like getting to smallholder farmers is incredibly hard, right? And getting information out of the more rural you are, the harder you are to talk to. and so of course your interventions have to be designed around what people might consider doing and what the incentives actually are. So I think our role at the moment is to, you know, give these best estimates and these best pieces of the puzzles to reduce the uncertainty a bit, but we can't ultimately tell people exactly what to do.
Yeah, exactly, which is the risk often, right? Would anyone like to ask any more questions or make any more comments? That we have a great group of interdisciplinarity, so that'd be great. Anyone else? No. David, that was great, and I have a couple of things to follow up with you, so I'll do it separately.
Sure.
With a couple of ideas that jump up into my head as you were talking. So I'll do that later. But if nobody else has further questions or comments, David, would you like, lots of people I see in the chat are thanking you for a great they will have to run to other meetings as always. But unless you have any further points to make, David, to wrap up.
No, I mean, if anyone wants to talk about either of the things I worked on, they're
and you
welcome.
had also a recent article, right? That
yes,
I had
well,
to hold on to before publishing.
Well,
website,
so it's still in bioarchive, but then waiting for reviews in the actual publication.
Okay, so as soon as it's out, then we can share it with the group.
Yeah,
that'd be great.
Well, it's already on bioarchive. Yeah, that could be shared.
Okay, and then it could be heard already. Okay, excellent. Thank you. I'll do that then. Well, then have a good weekend. Thank you so much, David, and I will see you next Friday.
Thanks.
Hopefully. Thank you. Thanks. Bye-bye.
Bye.